So today I will be talking about asymmetric domino synthesis of chiral heterocyclic compounds using organocatalysts. I think there's no need for me to give introduction about organocatalysts. I think starting from yesterday first talk by Professor V.K. Singh. Of course, I'm students of Professor V.K. Singh, and till now Professor Biju has given a lot of the excellent result using organocatalysts. But today I will be my work, which we have started just 2 or 3 years back, I will be very briefly presenting in today's lecture. At IIT Madras, my research group for the last 20 years working in the area of organic synthesis and catalysis. Mainly we work in the area of developing new reactions methodologies, and also we work in the area of catalysis, both homogeneous and heterogeneous catalysis. So we work in the area of chiral catalysis and transition metal nanocatalysis and halogen bonding catalysis. In today's lecture, I'll be talking about one of our recent project which we started just 2 years back. This is chiral catalysis. Again, I don't need to give too much introduction about chiral catalysis, but for students, chiral catalyst generally we use for asymmetric synthesis. Asymmetric synthesis means making chiral compound in enantiomerically enriched form. So there are 3 types of catalysts. The first one is enzyme catalysis. It's also, you can say, nature's catalyst, generally used by biosystem, including our body. And second one is transition metal, chiral metal catalysis. We say that generally we use transition metal and use chiral ligand and make a chiral complex, use them as a catalyst for asymmetric induction. This is quite established area, started from 1960s and 70s, and 2001 Nobel Prize was given to this particular area. Generally, I work in the area of transition metal chiral complexes for asymmetric synthesis. Just I would like to give a very brief one-slide introduction to our work which we are doing for the last 20 years. Around 15-20 years back, we wanted to mimic this galactose oxidase, which is having copper in the active site. So there are so many models were reported in the literature, but most of them are either achiral copper complex or racemic one. Being as organic person, particularly the asymmetric synthesis person, what I thought, when the enzyme has a copper in a chiral environment, why don't you make a chiral copper complex, that is galactose oxidase enantiomerically pure model? And if that is the case, we can use for oxidative kinetic resolution. So for the first time, we made a galactose oxidase chiral model with some deviation, obviously, by using this binam copper complex, and we utilized as a catalyst for oxidative kinetic resolution of benzoin. But that particular example, the selectivity factor for kinetic resolution, generally we use the efficiency of the reaction by the factor called selectivity factor. That means the rate difference between both the enantiomers of the starting material. It was somewhere around 10. So to improve the efficiency of the kinetic resolution, we tuned the catalyst. Then we developed a new chiral cobalt catalyst by tuning the catalyst structure further. And in this case, we were able to improve the selectivity factor from 10 to 47. And also later on, we were able to develop a new iron and zinc complex for same oxidative kinetic resolution. And in the case of kinetic resolution, you know that the yield, just now our previous speaker also spoke very briefly about kinetic resolution, dynamic kinetic resolution. Particularly kinetic resolution, the yield will be not more than 50%. So that's the drawback of this particular project. Then we wanted to develop the same product by using a reduction reaction where we can get more than 50% yield. So we are able to make the same type of compound by asymmetric ketone reduction by similar kind of catalyst. And also we have developed a new catalyst, the chiral ion catalyst, for the asymmetric hydrophosphorylation. This is really very excellent result from our group, but unfortunately the EE we are not able to increase more than 71%. And the same chiral copper complex we have used for oxidative coupling for the synthesis of biaryl compounds. And also the same time we have developed a new kinetic resolution by using similar kind of catalyst. Instead of palladium, copper, we use palladium. There's a coupling kinetic resolution. Again, it's a very nice reaction where the selectivity factor is not more than 4 or 5. So after working for more than 20 years at IIT Madras by using metal chiral complex, recently we started working in chiral organocatalysts, and that's the third type of catalyst for asymmetric synthesis. And 2021 Nobel Prize was given for asymmetric organocatalyst. Though that is a latest entry in the area of chiral catalysis, but this is, if you see the literature, The organocatalyst is known for more than 150 years for the A chiral one, and particularly for the chiral one is known for more than 125 years. They use the alkaloid organocatalyst for asymmetric induction. Initially the E was not very much, but slowly they increased, and the breakthrough really, though in the mid 90s PTC came in the picture starting from 1980s, and chiral DMAP catalyst or She catalyst came in 90s, but breakthrough happened in 2000 and 2021. The Nobel Prize was given to Benjamin List and David Macmillan. So these are some of the important example for chiral organocatalyst. You can see it here. The simplest one is proline, where it was extensively used by Benjamin List. Then you can say this is imidazolidinium catalyst used by Macmillan. This is alkaloid catalyst known for more than 120 years. This is the DMAP chiral type of analogs developed in 90s, and you can see it here. This is very popularly now you can see it in urea based hydrogen based organocatalyst, and peptides and so many, so on and so forth. This is also the She catalyst developed during 90s actually. So when we started this project around 2 years back, this was our target. We wanted to synthesize this pyrrolobenzothiazine. You can see it's a very interesting molecule. It's a fused tricyclic molecule having 3 continuous chiral center, and particularly this chiral center is a coronary chiral center, and you can see it is quite labile. If you want, you can do a retro-ultrasound, open it, and you can get another interesting chiral molecule. So if you see the literature, there are several similar molecules are available in the literature. So we wanted to make this molecule starting from this benzothiazonium salt and alkane by doing a 3+2 cycloaddition. And if that happens, you can see it here. This particular, the 5-member ring can be synthesized by using 3+2 cycloaddition, where this particular green, this portion comes from the double bond, and whereas this is a dipolophile and this is a dipolar. You can see it here. And once this ring is formed, if you are able to cleave this carbon-sulfur bond, then it will go here and do aldol reaction here to create the 3rd chiral center. So what we did before we start the reaction, so we thought we will add a carbonyl group here to the dipolophile. So in that case, the reaction can be much facile, and also we will have a handle to use organocatalyst. If you use a proline type of catalyst, then it will be very easy for us to do in asymmetric version. Indeed, if that is the case, then we will have an additional handling here, the enone or enol, where it can be further functionalized. So when we started this reaction, initially we used proline. You can see it here, 10 mole percentage. When we used, the reaction took place nicely at room temperature. The first attempt we got 24% of this particular product with 16% yield and single dash shimmer. And also in this reaction we obtained this particular the N-aldehyde 10%. Most of the reactions we get it. So this is happening not by 3+2 cycloaddition. It's a quite active molecule. If we have a little bit moisture in the reaction, it adds here, then CS bond is getting cleaved, against further oxidation, again closing here, it gives as a byproduct. So if you are able to avoid moisture in the reaction, then it will be possible for us to suppress the formation of the byproduct, so that the yield of this particular product can be increased. So to increase the efficiency of the reaction in both the ways reactivity and selectivity, we have carried out several screening process. You can see it here, several catalysts we have screened. Some of the examples we have represented here. Particularly when you use this Jorgensen-Hayashi catalyst, the yield from 24 increased to 52, and yield increased from 16 to 90, and the byproduct, the side product yield reduced from 10 to 5%, and further optimization by using replacement base triethylamyl by DMAP. Again, the yield increased further to 72, and E also increased to 98, and not big difference in the side product. So when we replaced the solvent ethanol by isopropyl alcohol, again further the yield is improved, and E is almost close to 99%, and you can see it here, the side product formation is almost minimized. There's no side product, we have not seen anything here. So this is our optimized reaction condition. So when we use this particular that Hayashi's catalyst 20 mole percentage. The reaction proceeds nicely at room temperature. After 74 hours, we are getting 87% yield and 99% enzyme excess, single diastereomer, and the absolute stoichiochemistry, as usual way, we have determined by using single crystal XRD. And you can see it here, this particular reaction by using the catalyst, we are getting all centers yes and yes, yes, actually we get it actually. And to know the efficiency of the reaction, we have carried out the reaction with several substrate. You can see it here. When we made variation in the salt, the reaction in almost all the cases, the E was more or less 95 plus, and you can see it here. There's no change in the E, and particularly when we have an electron withdrawing group, the yield slightly increases further, and the yield also in some cases, particularly here, the yield also increases from 78 to 90%. You can see it here. And also when we make the variation in the alpha beta unsaturated aldehyde case, particularly when we have the heterocyclic here instead of the RL group, the yield and E slightly reduces. Instead of the aliphatic one, if you aromatic one, if you take aliphatic, with methyl case, the yield slightly reduces, E is also reduces, and when case of ethyl and tertiary the E is going back to 90 plus, but yield is going down. So what we did then to understand a little bit more about the mechanism, we have carried out several control experiments. So under the optimized condition, when we carried out the reaction with simple proline, the yield is slightly reduced, but enantiomer asymmetric induction was drastically reduced to 12%, which shows the ester moiety is quite important here. When the TMS ether, the diphenyl tertiary alcohol ether is important for the asymmetric induction. So the same proline, when we protected by a Bock group, the yield is further getting reduced, and obviously the reaction gives racemic product, which shows that the iminium salt formation is crucial in this reaction. Then when we used the typical catalyst but protected form, N-protected form, the yield is further going down, and obviously is giving the racemic product, which shows that again the free NH is very important. The same reaction when we carried out with base, the reaction is not taking place, which shows that base is very crucial to carry out the reaction. But when you carried out the reaction only with base without the organocatalyst, still the reaction takes place and it gives the racemic product. And the message is when we use only base, there's a background reaction or the reaction takes place without making the iminium salt. With the aldehyde itself, the reaction is taking place. If you are careless, then there will be a background reaction, the asymmetric induction will go down. But in our case, mostly we get more than 95% enantiomer excess, which shows that when we use the organocatalyst, the iminium salt formation faciles the asymmetric version rather than the background reaction. So the take-home message, the base is very important to carry out the reaction, but when you use the catalyst, the background reaction is much, the rate of the reaction of the background reaction should be slower than the iminium formation type of reaction. And free NH is very important for asymmetric induction. And our bulky, that diphenyl TMS ether is crucial for higher asymmetric induction. So this is the proposed mechanism based on the literature report and some of our control experiment, and also supported by our DFT calculation. So initially the deprotonation will take place by the base to give this dipole. The same time the iminium salt will be found from alpha beta unsaturated aldehyde and catalyst. Then there will be a 3+2 cycloaddition from here to here. You can see this is the first crucial step where the asymmetric induction, the first cis bond will be forming. So you can see it here. This is the iminium salt where the diphenyl TMS ether will be below the plane, and there are two options where the dipole can approach from the beta phase, or it can approach from the alpha phase. Since we have the huge bulky group here, so the approach from the alpha phase may not be very much favorable, whereas the approach from the alpha phase will be favorable, which shows that there's an energy difference between both the transitions somewhere around 4.6 kilocalorie, which leads to very high enantiomeric excess. So once this first carbon-carbon bond is formed, then it will be going for the second carbon-carbon bond formation. You can see it here. Then under the reaction condition, this iminium functional group will be cleaved to give the 5-member ring. So once the 5-member ring is formed, this ketone, so this acidic proton will be deprotonated to give this enolate, and this will be going back to open or cleave this carbon sulfur bond. And once this bond is opened, you get the thiophenolate, and that it will go for CN bond formation. There are two possibilities. So there's an aldehyde, there's a carbonyl group. In a typical manner, if it goes for 1,2 addition, it should go for a carbonyl addition to a ketone carbonyl group, aldehyde group. But if it goes here, this is a 7-member ring formation, whereas it adds here, it will be a 6-member formation, where the energy for the 7-member ring formation is really it's a high energy process, whereas the 6-member ring formation is a energy the barrierless reaction. So there's a there's a CN bond rotation. It goes backside and attacks in a 1,2 fashion in an aldol reaction to give the particular CS bond formation to give the 6-member ring. So this is a way what we are expecting that there's an alternative way. Instead of this iminium bond getting cleaved, so it can be carried out, and the last step it may be getting cleaved. But again, the computation calculation shows that there's a possibility that first here it will be hydrolyzed, then aldehyde will be free aldehyde will be generated, and so on and so forth. This way, the reaction will be proceeding. And this whatever we have proposed also supported by the computation study, and we collaborated with our colleague Dr. Subramaniam. And what we have realized here that the iminium salt formation will be the rate determining step. So after making this particular tricyclic product, what we thought, so for this tertiary alcohol, this thiohemiacetal is a quite labile. And in fact, if you keep it for a long time, slowly it decomposes. So what we thought, if you treat with a base, then it will be deprotonated, then retroaldol, the ring will be opened up. And if you are able to trap by an electrophile, then we will be able to get, for example, methyl chloride if you use, then we will be able to make this very important, the tetra-substituted dihydropyrrole. This is also very important product present in several natural products. So when we carried out, they have taken our product and treated with base methyl iodide, DMF. You can see it here, 90% yield. It gave the E is also more or less same. So it looks very nice, very interesting product. But a typical organic chemist will not appreciate, because taking 3 chiral center and opening it, destroying the third chiral center. So what we thought, it doesn't look nice. So we are starting this particular product from readily available starting materials. So can we try in a one-pot manner so that it doesn't look that we are destroying one chiral center. So then we directly wanted to make this tetra-substituted dihydropyrrole in a one-pot manner, so that we will not see that getting one chiral center getting destroyed. So, and it happened when we treated both, and the product is formed, and without isolating, when we remove the solvent, add the DMF, then treat with alkyl halide and base, the reaction works very well, and it gives more or less same yields on EE whatever we are getting from the first 3+2 cycle addition, followed by ring opening, ring closing, now deprotonation and alkylation. So it happens, now you can see it here, the substrate scope is really very high. So to see the utility of this methodology, so we were trying to explore the functional group conversion. You can see it here now. When we treat with DDQ, the aromatization is taking place, and of course the chirality is destroyed here. Or if we have a halide here, we can do a coupling reaction, we can get further functionalization, we can do it here. And interestingly, when we wanted to oxidize this double bond, this position, bringing a double bond here by using DDQ, another surprising reaction we have observed here. What happens here? First, some is getting deprotonated. This ring is getting opened up by retroaldol. Then it goes and adds here in a 1,4 fashion, and followed by oxidation. it gives a very interesting, again, achiral product in the initial case. And there's a possibility for axial chirality. That's what we thought. So when the R is hydrogen, it's not a axial chiral product, whereas the R is bromo, then it is giving the chirality. But of course, what we got is not a chiral product. We got fully racemic. So first it goes for aromatization, then by the time, then later on. So the chirality is not retained. So now we are trying to synthesize this molecule in enantiomically enriched form in a different method. That is now presently going on. And as I told you, sometimes this product is not very stable. If you leave it for a long time outside at room temperature, it goes for it is decomposing. So then when you protect this hydroxy, the thiohemiacetal, this is quite stable. So we are able to protect with a good yield. And also we are, as I told you, when you have aldehyde here, this can be reduced selectively or completely, and we can further functionalize. That also happens very, very nicely. So then what we thought to extend the substrate scope of this particular starting material, instead of benzothiazonium salt, just very simple, just to add one example in the substrate scope, we have taken benzothiazonium salt, thiazonium salt, not benzothiazonium salt. This is when we use benzothiazonium salt, we get this particular product which I have discussed for last 15-20 minutes. So now, just see the only one difference here. This phenyl group is not here. Just we have a substitution here. So what we thought, instead of this tricyclic, we'll get a bicyclic. Remaining everything should be same. I don't think there will be any difference. But to our surprise, when we carried out the reaction, the product, we didn't get it. And what we got is completely aromatized tri-substituted ferrol product. And when we were doing the reaction, we could feel that thiophenol smell here. And when we carefully monitored the reaction by the GCMS, we are able to confirm, not only by the smell, also we are able to confirm that in this reaction, this particular thioketone is the byproduct. So again, what to say? This is the product is not a chiral one at this thing when we don't have huge substitution at ortho-DAS position. So what we thought initially, we'll use a racemic catalyst, then we can make a tri-substituted compound, and just to check whether this methodology is useful, make tri-substituted ferrol. Then we have realized that when we were studying the mechanistic path of this reaction, then we have realized that this reaction goes through this tri-substituted dihydroferrol, which can, if you are able to stop the reaction at this stage, then it's a chiral product and it will be a very useful product. And fortunately that we are able to control the reaction. So when we are able to do the reaction instead of room temperature, when you control the reaction at 0 degrees centigrade with a little bit more other things, we are able to stop the reaction at this stage, dihydro tri-substituted ferrol, and we are able to get up to 98% enantiomeric excess. And the substrate scope is really very, very good. By changing a lot of variations with the salt, we are able to get very good yield and EE. And similarly, by changing the variation with this alpha-beta unsaturated aldehyde, the reaction works very well. So what we have realized, so what makes the difference? The only thing is the phenyl group is there. So how it is completely changing the course of the reaction. The first part of the mechanism is exactly same. Then what happens here? Once we have the CS bond is opened here, for example, a deprotonation, then it opens. Now we are getting vinyl thiolate in this case. But previous case, what we are getting, since there's a aryl group here, so we are getting phenyl thiolate here. So the difference is in this case, what we are having is vinyl thiolate versus phenyl thiolate. So that, I think what I am understanding, this particular phenolate is quite stable. When it is forming, then it is not getting protonated. It rotates and goes for the 1,2 aldol addition. Whereas in this case, it may not be very stable. So it will be immediately protonated. And then once it is protonated, again this enamine is getting protonated, iminium salt, then water molecule in the reaction is adding here, and finally this CN bond is getting reduced, and that will be leading to this dihydro tri-substituted ferrol. And if you are not able to control, it will be aromatized. If you are able to control, then we will be able to isolate this product in anisomically enriched form. So that's what happened in the finally. So when you use the chiral catalyst, and if you are able to stop this, trap the intermediate, particularly at 0 degree centigrade, it happens, and we are able to isolate this compound in anisomically enriched form. If you are not able to, if you are not stopping it, then slowly it's getting aromatized and ending up with this aromatic compound. So to conclude my talk, so for the last 2 years, by using this Jorgensen-Hayashi catalyst, we were able to make the tricyclic benzothiazonium, the tricyclic compound, which is having 3 chiral center, starting from a 3+2 cycle addition, followed by ring opening and followed by ring closing reaction domino methodology. And this same reaction, if you treat this product with a base followed by electrophile, so we were able to nicely cleave this bond and trap with the electrophile to get the tetra-substituted dihydropyrrole with a good with good anisomeric excess. And instead of taking this benzothiazonium salt, if you take only we can say the thiazonium salt, then it completely, not only after 3+2 cycle addition reaction, not only this CS bond is getting reduced, in this case the CN bond also is getting cleaved to give a completely different product, that's a tri-substituted pherol. And if you are able to do the reaction in a controlled manner, then we were able to avoid this aromatization and we were able to get this particular anisomically enriched product. So with this I would like to thank my collaborator, Professor V. Subramaniam, who is supporting us for the computational calculation of our reaction propose mechanism, and the whole work whatever I have presented, that work was carried out by Dr. Pandidurai, who has defended this work 2 or 3 months back. Next month he is going to France to do his postdoctoral work. With this I thank you all for listening this presentation. Thank you very much.
We have time for a question.
Yeah, nice. Very nice talk, Sekarji. So I have a question related to your control experiment in the first half. You did a reaction with the Bock-protected Hayashi-Jorgensen catalyst, and the selectivity was not observed, but still the reactivity was observed, or the product was formed in 45% yield.
Yeah.
So how the reaction works in that case?
No, what we are expecting, without that case, maybe even iminium salt may not be forming. Okay. Even if you have a aldehyde, it's a blank reaction, then it will go for 3+2 cycle addition. Okay, so the beta position addition of cinnamaldehyde is happening without the iminium salt. Okay. That's the one main reason.
Okay, and another question is, so when you are working on this benzothiazolium salt under basic condition, did you ever generate or form the carbenes out of it?
No, we have not seen anything like that. As soon as we treat with the base, I think the dipole is formed. Since we have activated olefin, it goes for 3+2.
Okay, so there is no
we have not, maybe some minor quantity followed by some kind of something which we have not observed.
Triethylamine can still generate the carbene, the benzothiazolium carbene can be generated using triethylamine.
Yeah, that's what we are also thinking about that. But here it's very, very nicely, it goes for 3+2.
Okay.
It's a quite facile reaction.
Okay.
We are also thinking about that, but it's not happening.
Yeah. Thank you.
+2 cycle addition, you are getting exclusive SNS.
Yes.
You are not getting any other diastereomer.
No.
Okay, so the reaction is 100% diastereomer selective, 100% anesthetic.
Yeah. I will not say 100% anesthetic selective, because you are seeing 94, 95, 98. So it's highly diastereomer selective.
Highly diastereomer selective.
That's what I will say.
Okay, sir. Thank you.
Okay, so please join me again to thank Professor Sekar and Professor Bijou for the conference.
Long live India and France friendship.